Hey everyone, welcome back to the channel. Today we're diving into something that could fundamentally change how AI models handle long documents and contexts. Deepseek just dropped their OCR model, and it's not just another document reader. It's a glimpse into how we might solve one of AI's biggest challenges, the computational cost of processing massive amounts of text. If you've ever wondered, why can't AI just look at a picture of text instead of processing every single token? Well, Deepseek just asked the same question, and the results are fascinating. Let's break it down. So what exactly is Deepseek OCR? At its core, it's a vision language model designed to read and understand documents. But here's where it gets interesting. The researchers built it specifically to explore optical context compression. Think about it this way. When you read a document with 1,000 words, your language model needs to process 1,000 plus tokens. But what if you took a picture of that document? That image might only require 100 vision tokens to encode. Deepseek OCR consists of two main parts: DeepEncoder, a novel vision encoder that processes images efficiently, even at high resolutions, and Deepseek 3B-MOE, a compact 3 billion parameter decoder with only 570 million activated parameters. The model can handle nearly 100 languages, parse complex charts and chemical formulas, and most impressively, it can achieve 97% accuracy while compressing text at a 10x ratio. Even at 20x compression, it still maintains around 60% accuracy. Let's talk about what makes Deepseek OCR special compared to previous OCR models. Most vision encoders face a brutal trade-off. You either get good quality with massive computational costs or efficiency with poor results. Deepseek solved this with a clever hybrid approach. DeepEncoder combines an 80 million parameter SAM model for local perception using efficient window attention, a 300 million parameter CLIP model for global understanding with dense attention, and a 16x compression module that bridges them together. What this means in practice, they can process a 1024 by 1024 image as 4096 patches initially, but the window attention keeps memory manageable. Then, before hitting the expensive global attention layers, they compress it down to just 256 tokens. Brilliant. Here's something really clever. They built the model to support multiple resolution modes simultaneously. You've got tiny mode at 512 by 512, giving you 64 tokens. Small mode at 640 by 640, giving you 100 tokens. Base mode at 1024 by 1024, giving you 256 tokens. Large mode at 1280 by 1280, giving you 400 tokens, and Gundam mode with dynamic tiling for ultra-high resolution. This lets you dial in exactly how much compression you want versus accuracy you need. Testing a simple document? Use 64 tokens. Need high precision? Scale up to 400 or use dynamic tiling. The researchers ran extensive tests on the Fox benchmark, documents with 600 to 1300 text tokens. The results are eye-opening. At 7 to 10x compression, you get 96 to 98% accuracy. At 10 to 12x compression, you're looking at around 90% accuracy. Even at 20x compression, you still get around 60% accuracy. This isn't just academic. It proves that optical compression is viable for real applications. But does it actually work on real documents? The answer is yes. On OmniDocBench, a comprehensive document parsing benchmark, Deepseek OCR beats OCR 2.0 while using fewer tokens, 100 versus 256. It outperforms Miner U 2.0, which uses over 6,000 tokens per page, while Deepseek OCR uses under 800. It achieves competitive performance with models like Intern VL3 and Qwen 2.5 VL that use 4,000-7,000 vision tokens. And here's the kicker for production use. A single A100 GPU can process 200,000 plus pages per day. That's document processing at scale. The model also supports what they call deep parsing. It can automatically detect and extract structured data from charts, chemical formulas, geometric figures, and even natural images within documents. One unified prompt, multiple capabilities. Okay, so why does this matter beyond just better OCR? Current LLMs struggle with long contexts because of quadratic computational scaling. If you're having a 50-turn conversation, that's thousands of tokens of history the model needs to keep processing. Deepseek OCR suggests a radical alternative. What if we rendered old conversation history as images and compressed them optically? Recent turns stay as high-fidelity text, but older context gets progressively compressed into lower-resolution images. It's basically a forgetting mechanism that mimics human memory. Recent stuff is crystal clear, older stuff gets fuzzier. This could enable theoretically unlimited context windows, while keeping computational costs manageable. More immediately practical, Deepseek OCR can generate training data for other LLMs and VLMs at massive scale. 200,000 pages per day means you can process entire libraries of books, academic papers, and documents to create high-quality datasets. Now, the researchers are appropriately cautious. They acknowledge this is early-stage work. OCR benchmarks alone don't prove that optical compression works for general context. They'll need to run actual long-context tests, like needle-in-a-haystack experiments, with mixed text-image inputs. There are also interesting questions about what happens at higher compression ratios, how well the model preserves semantic understanding versus just character-level accuracy, and whether this approach scales to other modalities. Deepseek OCR is open source. Code and weights are available on GitHub right now. Whether you're interested in document processing, building VLMs, or just curious about novel approaches to AI efficiency, this is worth checking out. The bigger picture here is fascinating. We might be looking at a fundamental rethinking of how AI models handle information. Instead of everything being tokens in a sequence, we could have this hybrid world, where information exists at different resolutions, based on how important and recent it is. What do you think? Is optical context compression the future, or just a clever trick for documents? Let me know in the comments below. If you found this interesting, definitely subscribe for more AI research breakdowns. I'll be tracking how this space evolves, especially if we start seeing LLMs with these hybrid text vision memory systems. Thanks for watching, and I'll see you in the next one.